All right, next I'd like to look at another F equals ma, torque equals I alpha combination problem. And in this one, we're going to revisit the Atwood's machine problem. I know a lot of you weren't satisfied with the last solution because we didn't include pulley mass. And so this time we're going to do that. And we know how to do that because we can look at the sum of the torques acting on the pulley. That's equal to I alpha. And we can look at the sum of the forces acting on M1 and M2. And so that's going to give us three different equations. Okay, and so the question then is that how many unknowns we have? Well, it turns out yeah, because the tension here pulling up on M1 is not the same as the tension here pulling up on M2. Why? Well, before it was, but that's because we were neglecting pulley mass. And so now, this tension not only has to lift this mass, but it also has to accelerate the pulley. And the pulley has rotational inertia. So that means that this tension, T2, must be greater than this tension, T1. And so therefore, not only are they unknowns, but they're different from each other, in which T2 must be greater than T1. But they're unknowns. And then we have a third unknown, which is the acceleration. So that means that when we're solving, we need to have three equations, but that's exactly what we get. Two force equations, one for M1 and M2, and a torque equation for the pulley. So that's where I'm going to go with this. I usually like to start with the force equations first. So let's look at M2. Now M2 is going to have a bigger force acting downward than up because we know that it's accelerating this way because M2 is greater than M1. So that's going to cause an imbalance that'll make it accelerate this way. M1 will rise as the pulley rotates clockwise. All right, so for M2 then, we have the sum of the forces equals MA. And so that's going to give us M2G minus T2 equals M2A. And then for mass 1, we'll define the positive direction as up, which means that even though T1 is smaller than T2, it also has to be bigger than M1G. Because that's the only way for the M1 mass to accelerate upward, is to have T1 be greater than M1G. So for M1 then, we've got T1 minus M1G equals M1A. So those are our force equations, but we also have a torque equation. Sum of the torques equals I alpha. So remember that we do in fact have a normal force here of the pivot of the whatever the support is on the pivot. But we don't really need to worry about that if we again choose for this fixed pulley the center of spin to be right at the center of the pulley. Then we actually have two torques acting because we have one torque is acting this way. T2 is the same as the T2 here, but because of Newton's third law, it points away from the tangent to the surface there. And then T1 is smaller, and so that acts this way through this radius vector. Okay, so T1 is creating a counterclockwise torque, but T2 is creating a larger clockwise torque. Since we're defining the positive direction being the direction of motion, that's in the direction of the clockwise torque, T2R. So we can write this then as T2R minus T1R equals I. Remember, that's the moment of inertia at the pulley. Let's once again assume that the I is a cylinder, or 1/2 mR squared. You might be wondering, is it ever not a cylinder? The answer is yeah, lots of times, most of the time. But a cylinder is a nice, easy shape for us to work with. So this is going to be 1/2. This is the mass of the pulley times r squared times alpha, which again is A over R, for the same reasons as discussed earlier. Canceling out the factors of R, we get T2 minus T1 equals 1/2 big M times A. So that's our third equation. This is equation 1, 2, and then this is equation 3. And so this looks like a pretty big mess, doesn't it? Because we've got T1, T2, and the acceleration is our unknowns. But no, not if we choose the positive direction to be the direction of motion. We'll just put them all right one over the other and just add them together. And all the coupling tensions will cancel. We get here T2 minus T1 equals 1/2 big M, which is the mass of the pulley, times A. That's equation 3. When we add all three of these together, notice here that almost by magic, the T2s cancel, the T1s cancel. And so what we're left with then is a composite equation that looks like M2G minus M1G equals little m1A plus little m2 times A plus big M times 1/2 times A. Because here we had 1/2 MA. So I'm just adding all three of these together. Or this is M1 plus M2 plus 1/2 big M times A. And on the left-hand side, that's M2 minus M1 times G. So this gives us our final expression for the acceleration as equaling M2 minus M1 divided by M1 plus M2 plus 1/2 big M times G. All right, and so you may recall that when we had solved for the acceleration before of the Atwood machine, but without pulling mass, we got M2 minus M1 divided by M1 plus M2 times G. And so we see then that if we neglect the mass of the pulley, that's exactly what we have here. But because we are including the mass of the pulley in this calculation, that creates a bigger denominator, which makes the acceleration lower. But that should make intuitive sense because the system is going to rotate more slowly if there's more inertia in the system. Okay, and so with the values of M1 and M2 that I've given, 2 for M2, 1 for M1, we've got 2 kilograms minus 1 kilogram divided by 1 kilogram plus 2 kilograms plus 1/2 times 2 kilograms times G. Or dropping the units in the last step, we have 1 divided by 1, 2, 3, 4. So this gives us G over 4 for our acceleration, using those numbers for the Atwood machine. Okay, now next what I want to do is to introduce the concept of rotational kinetic energy. And so you'll notice then in the data projector slide, we have some correspondences here that I wanted to point out to you between pure translation, which just means motion of the center of mass, and pure rotation, which is motion about the center of mass. So position becomes theta, velocity becomes omega, acceleration becomes alpha, mass becomes moment of inertia, then F equals ma becomes torque equals I alpha, work, the integral of F dot dx, becomes work done by torque, which is the integral of torque times d theta, because F is replaced by torque, and x is replaced by theta. And so isn't that interesting, that the work done is equal to the torque times the change in the angle. Okay, so let's take a look at that for a second. We know from our translational type of motion that work equals the integral of F dot dx. But we can easily convert this into a torque problem by thinking of the dx as being a d arc length. And so if this becomes a d arc length, then s is equal to r theta, and ds is equal to r d theta. Okay. And so if we do that, then we can rewrite the system as work is equal to the integral of f. And let's assume that the cosine of the angle between the force and the displacement vector is 90 degrees, or it is 0 degrees. So cosine of 0 equals 1, so we just have f ds. In general, this would just be the part of the force that is in the same direction as the displacement. So if we had something like this, where the force is acting this way, this is our direction of the little bit of angular displacement, ds, then that would produce a pure torque. Okay? And so what we could do here then is say that this is the same thing as the integral of rf times ds over r. Okay? But ds over r is just d theta. And so this is the same thing then as the integral of torque d theta. So if we integrate a torque then to a certain angle, we do a certain amount of work. So let's say this force stays constant and is always acting perpendicular to the system and causes a rotational angle of 90 degrees. As we apply that force, always in the same direction as our little ds as we go around. Or you could have a little motor here that was powering a disk that was in static friction contact with this disk that was providing a constant force at just that location. That would be the same basic result. So for this problem then, let's say that the force is equal to 50 newtons and the radius is equal to 10 meters, then the torque would be equal to 50 times 10, or 500 Newton meter. And then if we apply this torque for 90 degrees, then this would be basically torque times the integral of d theta, because in this case the torque is not a function of theta. And so that would be equal to the torque times theta, evaluated from 0. And we need to have this in radian measure, as was the case before, and not in degree measure. So this would give us 500 Newton meters times pi over 2 radians. And so that would be equal to 250 pi joules. So that would be the amount of work that we would do in applying a torque to a certain angle. But remember that in order to do work, we require that the system must move. So just applying a torque is not the same thing as causing a change in the energy. You have to apply a torque through an angular displacement in order to do work. Now the other thing that I wanted to look at, if we can just look at this data projector screen one more time, is the idea of energy. You'll notice here that the kinetic energy in pure translation is 1/2 mv squared. But the kinetic energy in rotation, if we take the mass and replace it by the moment of inertia, take the velocity and replace it by omega, using that correspondence principle that I was looking at earlier, that gives us a kinetic energy that's equal to 1/2 I omega squared. So this is the kinetic energy of rotation. So with kinetic energy of translation, we just take the mass and replace it by the moment of inertia, the velocity replace it by omega, and that gives us this expression for the kinetic energy of rotation. Now that's not a derivation, but that is a correspondence that works. Here's the derivation. We can say that the work done is equal to the integral of the torque times d theta. And so then for torque, we know that torque is equal to I alpha. So this is the integral of I alpha d theta. But alpha is the derivative of omega with respect to time, but it's the second derivative of theta with respect to time, because omega is d theta dt. So basically, by taking the derivative of omega, what you're doing is taking the second derivative of theta. Okay. And so those are our connecting links here. The one that is going to help us the most in this problem is to write this as I d omega dt times d theta. Okay, so that's alpha. Okay. And so then, that doesn't look like it's helped us very much. But if I use the chain rule, we can see that this d omega dt can be rewritten in a more useful form for this problem. D omega dt is equal to d omega d theta times d theta dt. And so if I rewrite it that way, then we've got integral of I times d omega d theta dt times d theta. All right? So now we can cancel out the d thetas, and this becomes now an integral over omega of I d theta dt is omega, so it's I omega d omega, from omega initial to omega final. And so our work done then is equal to 1/2 I omega final squared minus 1/2 I omega initial squared. Or this is just the change in the kinetic energy of rotation. And so that's equal to the work that's done. Here I'm going to write work with a little feet on it so we don't confuse that with our omega. Okay, so this is just like our work done in the case of kinetic energy is equal to 1/2 mv final squared minus 1/2 mv initial squared. But now this is the work done to change the angular velocity of an object from omega initial to omega final. So it's like if I take this bike tire and I apply torque to this bike tire, fairly uniform torque, as it continues to increase its spin rate, I've changed its energy because the omega initial is different from the omega final. And so I did work to make that happen. And that's equal to the change in the rotational kinetic energy. Now, does energy of rotation do work? Well, we can see that here just by taking this bike tire and putting it down on the table. We can see, look at that. That moved the center of mass from 0 velocity to some final velocity. And so, yeah, rotational energy definitely can do work. And that work could be in a little generator on your bike. If you want to have a bike light, then a lot of times what you'll have is a little device that makes static friction contact with your wheel on the bike. And that causes a magnet to turn inside of a coil of wire. So that work done on the coil moving inside of the magnet is going to then be electricity that's generated. And that electricity then can light the light. And so that's doing work, and then that work is turned into energy. All right, so what I want to do next is expand on my energy equation, because now I've got a new kind of energy. I've got kinetic energy of rotation. So our expanded conservation of energy equation, if F external is equal to 0, then we have total initial energy equals total final energy. But now we've got one new energy term, which is the rotational kinetic energy. So we can write this as 1/2 mv0 squared plus mg y naught plus 1/2 I omega naught squared plus 1/2 k x naught squared, if we have springs in the problem too, equals our final energy, 1/2 mv final squared plus mg y final plus 1/2 I omega final squared plus 1/2 k x final squared. And then if we also have friction in the problem, then we can add plus the absolute value of the work done by friction. So this is getting to be a pretty big equation. And if we had to use all of these terms, it would be kind of daunting. But in most problems, we only use a few of these terms. And so in my next example, what I'd like to do is take a look at a problem that we've already looked at. That being a mass rolling down an inclined plane. So here we'll take the cylinder, and we've already looked at this problem from the standpoint of torque equals I alpha. We figured out the acceleration of the mass down the incline. But now let's use the energy equation to find the final velocity of the center of mass of this rotating cylinder going down the incline. So we have a rotating cylinder here, radius r, mass m, and it moves down an inclined plane. Let's say the angle here is 30 degrees, and the length here, L, let's say, is 10 meters. So that's the distance that the center of mass moves. And let's say that the initial velocity is 0, but now it's going to rotate. And so that means that some of the energy is going to go into rotational kinetic energy, and some will stay as center of mass kinetic energy. All right, so we can go back to this equation, and we can simplify considerably, because in the initial state at the top, that's up here, the initial velocity and the initial rotational velocity is 0, and y naught is equal to L times the sine of 30, or that's just L over 2. Okay, so I can get rid of this term, I can get rid of this term, and there's no springs in the problem, so I can get rid of that term automatically. In the final state, we'll call this point here y final equals 0. And we want to know what V final is, let's say at this point. So V final is a question mark, and we want to know what Y final is. Now we do have static friction rolling down this incline, but static friction at any given point does no work, because static friction is associated with there being no motion at the point of contact. Okay? And so if that's the case, then this thing is pure rolling motion, because as it rolls down, the tangential velocity equals the center of mass velocity, and so if you look at the velocity at this point, it's got to be 0. Okay? And so it's never moving at the point of contact, and so therefore there's no kinetic friction, only static friction, and the static friction does no work, because there's no motion. the static friction. So that term is gone. The final spring energy is 0 because the initial spring energy is 0. And mgy final is 0 too. So what we're left with then is a much simpler equation. Just potential energy, mgy naught, equals kinetic energy at the center of mass, 1/2 mv final squared, plus rotational kinetic energy, 1/2 I omega final squared. Okay, so our potential energy then no longer just turns into center of mass kinetic energy, but there's also a certain proportion of that energy which is invested in the rotation to get this thing spinning faster. And so that's different from the kind of problem we did before where the mass was just sliding down the inclined plane. In that problem, mgy naught was just equal to 1/2 mv final squared because there was no rotation. But here there is. So let's go ahead then and solve this. The masses are going to cancel. Now how do I know that the mass is going to cancel from this equation? Well, let me just simplify that first before I state that that's true. So this will be 1/2 mv final squared plus 1/2 I. I is 1/2 mr squared. If we again are using a cylinder here, so that goes in here for I. And then omega final is equal to v final over r. Just the same way as with acceleration, A tangential is A center of mass over r. That's the same thing with the final velocity. So now we are ready to cancel out some of these terms. The masses cancel all the way through. What we're left with then is just gy naught equals v final squared over 2 plus, and then the r's are going to cancel here. There we have one r canceling with that r, and then this should be squared, sorry. So that's v final squared over r squared. So the r squareds cancel here, so we end up then with v final squared over 4. So we can see then that the final rotational kinetic energy is only 1/2 of the final center of mass kinetic energy. And so that means that 2/3 of the energy has gone into center of mass kinetic energy and 1/3 has gone into rotation because that's in a 2-to-1 ratio, just like this is. Okay, and so the energy of the potential here, the gravitational potential energy, has 2/3 of that energy going into center of mass kinetic and 1/3 going into center of mass potential. So we can simplify this a little farther and just say that gy naught is equal to, on the right, that's going to be 2v final squared over 4 plus 1v final squared over 4. Or that'll be equal to 3v final squared over 4. And so therefore, v final, solving this equation for v final, we get that that's the square root of 4/3 gy naught. And now how does that compare with what we had before without rotational kinetic energy? Well, if we just had 1/2 mv squared equals mgy, then v squared would be the square root of 2gy. So here you see that it's a little smaller than that because some of the energy had to be invested in rotational kinetic energy. And so because of that, the center of mass kinetic energy didn't get quite as much. And so it differs by a factor of the square root of 2 times gy to the square root of 4/3 times gy. Okay, so finishing this up then, v final for this problem would be equal to root of 4/3 times g, 10 meters per second squared, times y naught. Now y naught, remember, is L over 2. L was 10 meters, so you don't want to accidentally plug in 10 meters here. It's just the vertical height that gives us the potential energy. And so that would be equal to 5 meters. Okay, so that would be the square root of 50 times 4/3. And so our final answer then for V final is square root of 200 divided by 3. Which is 8.16 meters per second. So that's our final velocity. Now you might wonder, how would this change if I had a ring rolling down the incline? What would be the final velocity of this thin ring? Well, recall that the thin ring has a moment of inertia that's equal to just mr squared here. So we'd have an mr squared instead of a 1/2 mr squared. This would be a V final squared over 2. So that means that there'd be a 50-50 split between the rotational kinetic energy and the center of mass kinetic energy. And that means that V final would just be equal to the square root of g times y naught, or the square root of 50. Okay, so V final would be lower. It would just be the square root of 50, and not the square root of 50 times the square root of 4/3. So it'd be a lower value than this, and so therefore the cylinder will win. And so let's just look at it again with that thought in mind. And with a higher moment of inertia, there's more energy that goes into the rotating of the thin ring than here. This is only 1/2 the energy of the center of mass. Here, the energy of the rotation is equal to the energy of the center of mass, and so that makes us more sluggish because it has a larger moment of inertia.